What we have done has been the following. We talked about controllers, then we said controllers are state machines, then we said some of them are more complex than others, then we showed a controller that, or a state machine, or a finite state machine that makes decisions and goes from one state to the other one. And we showed the state diagram of it, which is the front end of our design process, like a flow chart. And then we said, well, yes, we can always do that, write the finite state machine, or show the state diagram, and from there go into the very long description and turn it into hardware. But now let's look at more FSMs, starting from a state diagram and turning them into hardware manually. Okay? And since we are doing this manually, they have to be small. They have to be small, they have to have input, they have to have output, they have to have several states, and therefore I start with what is referred to as sequence detectors. Machines that detect a certain sequence on their input. Sequence detector. There are two types of sequence detectors. One is mealy machine, one is Moore machine. Actually, there are two types of finite state machines, mealy and Moore. They are different in the timing of the output. Okay? We start with the one that is more precise timing-wise, which is referred to as Moore machine, M-O-O-R-E. What I want to design is this. I want to design, don't look below, look at the green stuff there. I want to design a circuit that detects sequence of 1, 0, 1, 1 on its serial input, on the J input. This is the circuit I want to design. See? As soon as I say this, I say I want to design a circuit that starts in let's say initial state of it, and then it searches for 1011. When you say searching, that means it's looking for something. When it's looking for something, it means that it has to remember what it has seen and what it is expecting to happen, and therefore it means that this is a sequential circuit. It is a circuit that has memory. I won't be able to design a sequence detector using combinational circuits, because combinational circuits don't remember anything. This has to remember that a 1 has been received, and then it has to remember that the 0 has been received on the serial input of it. And then it says, after in 4 consecutive clocks, it finds a 1, a 0, a 1, and a 1 on the J input. For 1 exact clock period, it makes the output W1. Okay? And this is what my state machine is. This is what I'm designing. Okay? How do I go about this? Okay? I'm designing this. How do I go about this? Eventually, I have to turn it into Carnot maps. Eventually, I have to turn it into gates. And I know there are flip-flops there. But how do I get started with this? In the previous discussion, what we said was what? Well, we can get started by showing a flow chart of what we are designing, or a state diagram of what we are designing. A diagram representing the states of this circuit. What are the states? States are things that my circuit remembers. My circuit remembers it has not received anything, so that's a state. My circuit remembers that it has received a 1 and it's looking for another 0 that follows that. Okay, that's another state. My circuit remembers that it has received a 1, a 0, a 1, a 1. Okay, that's another state. Okay? So let's describe this state machine. okay, using a state diagram. And then go for designing it. Often the example I use is, let's say you've been told you're looking for an address. You've been told that there is a grocery store, then there is a flower shop right after that, then there is another grocery store, then there is another grocery store. After that, I mean, why there are too many grocery stores, let's not worry about that. But then after that, you turn right. Okay? So in your mind, you sit and you are driving. Okay? If you see a flower shop, what do? Well, you say, well, I have to see a grocery store first and then see a flower shop. Okay, so that flower shop just by itself means nothing to me. Okay, and therefore, let's say the grocery stores are 1, flower shops are 0. And therefore, if you are just driving, have started driving and you are in state A. State A is the state that nothing worth remembering has happened. Nothing worth remembering has happened. And then you see a flower shop in that. Is it worth remembering? No, because you have to see a grocery store first and then a flower shop. And therefore you don't change the state. See, the same thing, the way we think. The way we think is, if something happens which is not worth remembering, you don't change the state of your mind. If you're looking for buses, or if you're looking for a bus to arrive, if 10 taxis go by, you won't remember how many taxis have gone by. That means you are not changing the state of your mind. Here, I'm not changing the state of my circuit for zeros being received. Okay? And therefore, for as long as I'm getting zeros, for as long as I'm finding flower shops on my path, I'm not changing my state. As soon as the first grocery store arrives, or I arrive at the first grocery store, I say, oh, okay, so I have seen a grocery store, so let's change the state of the mind because it is worth remembering. I don't promise that this is definitely that grocery store that I'm looking for, but is worth remembering. And therefore, if I see the first grocery store, I go to state B where I remember seeing a grocery store. If I see more grocery stores, what happens? If I'm in state B and I see another grocery store, I say, oh, okay. So that first one wasn't really the grocery store I was looking for. This one may be the one that I have to look for a flower shop after it. And there, a second one, a third one, a fifth grocery store, you keep looping back into the same state. A 1 takes you back into the same state that one grocery store is saved. And more grocery stores don't change the state of your mind. This continues until you see the first flower shop after a series of grocery stores, maybe. The first flower shop, you say, oh, okay, I've seen a grocery store, 1 at least. And now I'm seeing a flower shop. That's good because I'm going in the direction of completing the sequence. And therefore, you go to state C where a grocery store followed by a flower shop. A grocery store followed by a flower shop are have been seen and worth remembering. If after the flower shop you see another flower shop, You say, I'm looking for a grocery, flower, and then a grocery, but then I saw a flower shop. What do I do? Well, I've been wrong all the time. This is nothing that I was looking for. Let's just start from scratch. And therefore, a flower shop takes you back to state A, where you are starting from scratch. Scratch looking for another grocery. So this wasn't what I was looking for. But on the other hand, if you're in state C and you see a grocery store, you get quite happy. You say, well, finally, I'm getting there. And then you go into state D. Okay, so state D remembers G, F, G. If you're in state D and you see the next grocery store, what do? You say, well, finally, a G, an F, a G, and a G, and therefore let's set the output to 1. Decision is made, the output to 1, that means your output becomes 1, that means you're going to turn right. On the other hand, if you are in state D, and state D was what? G, F, G, and then you receive a G, you receive an F. What do you say? Yeah, that's not what I was looking for, but that's not the end of the world. Because this part is according to the sequence I'm looking for. The GF is according to that. So maybe there will be another G, and finally I go to state E. And therefore, you go to the state where GF has been saved, which is state C. And therefore, a 0 in state D takes you back to state C. If you are in E, a G, an F, a G, and a G, and then if you receive an F, that can be the beginning of, now I don't have that address looking for the scenario anymore, okay? Now let's go to the reality and look at for ones and zeros. If I am in state E and I receive a flower, then that could be the GF of the next sequence. Okay, and therefore from E, if you receive a 0, you go to state C. If you are in E, that means a 1, a 0, a 1, a 1 has been received, and you receive another 1. Then you say, okay, that 1 may be the beginning of the next 1, 0, 1, 1, and therefore you go to state B, and then from then on you continue. Okay? That's my state diagram for this little controller, which I'm referring to it as a sequence detector. What's so good about the sequence detector is easy. It has one input, it has one output, and it has 4 or 5 states, and therefore it's manageable, manually manageable. I don't want to write the very long description of it. I want to do it manually. When I'm done, I will write the very long description of it. But first, I have to learn how to design this myself, using flip-flops, using gates, using wires, and things. All right, how do we go about this? How do we change this into a circuit? First of all, what does this look like? It has A, B, C, D, E. I don't really like that. If I want to turn this into gates, I have to have ones and zeros. Plus that, this diagram look doesn't correspond well with the way I have learned how to design circuits. I prefer tabular. So what I do is, this is my state diagram, which I'm going to mark. This is my state diagram. I say as the next step towards making a hardware out of this, I'm going to turn this into a state table. All there is to it is just take that circular things and turn them into a tabular list. And therefore, this becomes my state table. Okay, well, let's say this becomes my state table. How did I get this? Well, if I'm in a state A, look here. If I'm in a state A, by the way, when you are in state, when you want all the edges out of that state belong to that state. When you are in state a 0 takes you back to state A. Okay, let's do this. When you are in state A, a 0 takes you back to state A 1 takes you to state B. And in there, your output is 0. Okay? So that's all there is to it. You take each of these states and turn them into the present state, the next state for j being 1, and the next state for j being 0. And this is j. And that gives you the next state and the output. This I refer to state table. Okay? That was good because I turned this circular looking thing into a tabular looking thing. So that's one step closer to Carnot maps that I love to have. Okay? What is still preventing me from turning this into a Carnot map? What is preventing me is that Carnot maps have zeros and ones in them. What do I have here? I have A's and B and C and D. That's not Carnot map. So let's do something else. Let's make an assignment to each state. Let's, instead of A, put 0, 0, 0. Instead of B, let's say put 0, 1, 0. Instead of C, say 1, 1, 1, or whatever I like. Okay? As long as there are unique bit patterns, I'm fine. Okay? And then I replace them with ones and zeros. Okay, that would be good because I'm getting one step closer to Carnot maps, truth tables. Instead of A, I put 0, 0, 0. Instead of B, I put 0, 1, 0. How many bits do I need? Since I have 1, 2, 3, 4, 5 states, in order to have a unique bit pattern, I need 3 state variables. Okay? The state variables can be assigned, or the states can be assigned any pattern I like. I can do binary. In this case, I'm doing binary. I'm giving 0, 0, 0 to A, 0, 0, 1 to... I don't have to, but I'm doing this. And then 1, 0, 0 to E. Unique patterns. Then I take my state table, and for each state in the present state column and in the next state column, I replace, for example, D is 0, 1, 1. And therefore, this D is replaced by 0, 1, 1. This D is replaced by 0, 1, 1. Do I have any more Ds? No. And therefore, you are seeing the 0, 1, 1. This is your D. And then 0, 1, 1. There is a D there. Okay? C is 0, 1, 0. C is 0, 1, 0. look in the next states. Everywhere you have C, put 0, 1, 0. Here is a C, here is a C, here is a C, 0, 1, 0, 0, 1, 0, 0, 1, 0. Okay? Same thing with A, with B and everything. Let me do B. B is 0, 0, 1. In the next state, B, 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 B. Okay? This becomes my transition table. Remember, in the case of counter, I directly came down to transition table. That was because counting is easy. I said I go from 000 to 001, or maybe even if I'm doing down counting, that wouldn't be that difficult either. But in this case, I wouldn't be able to get this state diagram directly, or let's say this. I wouldn't be able to get this state table or this transition table directly from the problem definition. I had to go through this state diagram and then this state table. That's the next state. That's the next step. And then transition table. So I started with the state diagram. And then my state diagram, I turned it into state table. Then I made state assignment, okay, and I turned it into transition table. Transition table. The first step, the second step, the third step is transition table. I'm going towards turning this into kernel maps. All right, transition table looks pretty good. It has zeros and ones. It has a input column, and then it has the outputs and all that. Everything looks like a kernel map. There is one exception here, and that is kernel maps. You have input A, input B, input C, and then the outputs are W, X, Y. Here, my inputs are V2, V1, V0, and J. And the output W is good, is W. But then the other outputs are V2 plus V1 plus V0 plus what is this? Okay? These pluses mean timing. Means that this is really not my output. Okay? This is the output of the Carnot map after clocking. But the Carnot map can only tell me the output of a combinational circuit. This has timing in it. This table, this transition table, has flip-flop in it, is implying some kind of flip-flop here. I don't want that. What I want is Carnot maps can only work for combinational circuits, not for sequential circuits, and therefore transition tables have to be turned into something different. So what I do is I look at the transition table and say, okay, let's turn it into a combinational circuit. And therefore, you have to decide. If you want to turn it into if you want to turn it into a combinational circuit, you have to decide on the flip-flop type. You decide that I want to do T flip-flop. Then you say this. Then you say, okay, I want to turn it into flip-flop, a T flip-flop, and therefore if for a certain combination of inputs If the next state is not changing, the T input has to be 0. If the next state is toggling, the T input has to be 1. And therefore you say, okay, for this combination, the T input of flip-flop number 2 is 0, because it's not changing. 0, 0, see? 0 here, 0 here. The T input of flip-flop number 1 has to be 1, because there is a 1 here, there is a 0 here, it's toggling. And for flip-flop number 0, same thing, the T input has to be 0. For, let's look at another combination. For let's do this. For this and this combination of inputs, T2 has to be 1, T1 has to be 0, T0 has to be 1, because this is changing, the second one is not changing, this is changing, and therefore you put 1, 0, 1 on the T input, clock it, and then you get the 0, 0, 1 as your next state. That's if you decided to do T flip-flop. The beauty of D flip-flop, though, is whatever you put on the D input, clock it becomes the output. And therefore, if you decide that you want to implement this transition table using D flip-flops, the D inputs become exactly as the transition table. I call that my flip-flop excitation table. And therefore, my next step is coming up with excitation table. An excitation table depends on the type of flip-flop we decide to use. From transition table, D flip-flop is decided, you go to excitation table. Now look, I removed all those pluses. All I'm really looking at now is a pure combinational circuit. Okay? Maybe no, maybe I decided to do T flip-flops. Still, I would have, instead of D2, D1, D0, T2, T1, T0. Still, though, I would have combinational circuit. The excitation table would be different, which is not that difficult. Okay? But then you would be still having a combinational circuit. So the next step is coming up with excitation table. After you decide the type of flip-flop. Now what I have? Easy. I have D2, D1, D0, 3 outputs of a 4 variable of 3 outputs for 3 4 variable maps. Okay, 4 variables, because J is 1 variable, V2, V1, V0, the 3 other variables. But then my W doesn't have the J input, and therefore this has a 3 variable map. Nevertheless, these are Carnot maps. These are combinational circuits. Let's forget about the pluses. We will come back to it. Then I develop my Carnot maps. Okay? And all I'm doing is I'm making a transition from here. Okay? Let's say J0, 0, 1. J0, V2 0, V1 1, and V0 1. That means 0, 0, 1, 1. I want 0, 1, 0. 0, 0, 1, 1. 0, 0, 1, 1. I want 0, 1, 0. I just take those values and put them in these Carnot maps. We'll continue in a few minutes.